Hey everyone! Welcome to QuickLearn, the place where learning new skills is quicker than making a cup of coffee. If you're eager to absorb new knowledge without wasting hours, you're in the perfect spot. We're all about delivering those juicy bits of info that stick with you fast. Ready to dive in? Let's crank up the heat and get started. Today, we're taking a wild ride through thermodynamics, basically the rulebook for how energy and heat play together. Think of it like being a detective, but instead of solving crimes, you're cracking the case of energy flow. To make it a bit less scientific mumbo-jumbo and a bit more aha, we're going to use an acronym, HEAT. Each letter of HEAT will guide us through the basics of thermodynamics and make those tricky laws feel like a breeze. H is for heat transfer. Picture heat transfer as a high-energy game of tag where energy is the tagger. There are three ways it gets around: conduction, convection, and radiation. Conduction is like when you touch a hot pan, yup, that heat is jumping straight to your hand, no chit-chat involved. Convection is like stirring a pot of soup, heat moves through the liquid, making sure every bit of soup gets a taste. And radiation. That's how the sun warms you up, even though it's miles away, no need to hold hands. To figure out which heat transfer is happening, just ask: is there direct contact, conduction, is something moving around, convection, or is it just beaming through space, radiation? For example, in your cozy home, radiators use conduction to warm up the room. The hot water inside the radiator heats up the radiator itself, and then, voila, the room warms up through convection. E stands for energy conservation. This is the first law of thermodynamics, which says energy can't be created or destroyed, only transformed. Think of it like this: if you add water to a bucket, it either fills the bucket, increasing the water level, or spills out, doing some work. When you're checking out a system, keep an eye on where all the energy is going. If you can't account for it, you might have missed some transfers. For example, when you heat a pot of water, the energy from the burner makes the water hotter. The energy doesn't vanish, it just changes from burner energy to water heat. A is for absolute temperature. This introduces us to entropy, the measure of how messy or orderly a system is. Absolute temperature, measured in Kelvin, is like setting the thermostat for understanding entropy. The rule of thumb here is: higher temperature means more energy to spread around, which increases entropy. Always convert temperatures to Kelvin when you're calculating entropy changes. It keeps your calculations precise and your science spot on. For example, when ice melts, it turns from a solid, low entropy, to a liquid, higher entropy. Knowing the temperature in Kelvin helps us measure how the ice's order turns into a watery mess. T is for thermodynamic cycles. These are like the repeat button on your favorite playlist, but for energy processes. The Carnot cycle is a classic example that shows how heat engines operate. Here's the deal: a thermodynamic cycle is designed so that the system goes back to where it started. This is crucial for things like engines and fridges to work efficiently. When setting up or analyzing a cycle, make sure you've got all phases, compression, heating, expansion, and cooling, lined up and ready to roll. For example, a car engine burns fuel, adding heat, pushes pistons, doing work, and then expels exhaust, heat rejection. This cycle repeats, efficiently converting chemical energy into motion. Here is an example breakdown. Let's put heat to work with a refrigerator. Heat transfer. Inside the fridge, heat is transferred from the chilly interior to the warmer exterior using the refrigerant. It's a whole process of evaporation and condensation in those coils. Energy conservation. The fridge uses electrical energy to shuffle heat from inside to outside. No energy is lost, it's just changing from electrical to thermal. Absolute temperature. The fridge operates at temperatures well below freezing in Kelvin. The temperature difference between inside and outside is key for how well it keeps things cool. Thermodynamic cycles. The fridge uses a refrigeration cycle, kinda like the Carnot cycle, to keep removing heat from inside and dumping it outside, ensuring that your ice cream stays solid. Here are some book recommendations for learning more about thermodynamics. The Laws of Thermodynamics. A very short introduction by Peter Atkins. This book is like a cheat sheet for thermodynamics. It's short, sweet, and packed with easy-to-understand explanations that make complex principles as clear as your morning coffee. Thermodynamics, an Engineering Approach, by Eunice Sengel and Michael Bowles. This textbook is perfect if you're ready to roll up your sleeves and dive deep. It combines theory with real-world examples, making it an essential read for anyone who wants to really get the hang of thermodynamic principles. Statistical Thermodynamics, Fundamentals and Applications, by Normand M. Laurendier. For those who love to dig into the nitty-gritty of how thermodynamics works on a microscopic level, this book is a gem. It explains the statistical side of things, linking them to practical applications. As Albert Einstein once said, "Everything is determined by forces over which we have no control." So, embrace the quirks of thermodynamics, and remember, while we may not control every force, understanding these laws helps us dance through the energy world with finesse and flair. Thanks for hanging out with me as we demystify heat, energy, and cycles. Hit that like button, subscribe to QuickLearn, and let me know in the comments what you want to tackle next. Let's keep learning fast, fun, and effective, one bite-sized lesson at a time.